Review for chapter 13. Basically, we have three different kinds of mirrors. We have a flat mirror, and for a flat mirror, it obeys the law of reflection, so that when a light ray comes in, that's called the incident ray, and when it reflects, those two are always equal as measured from the normal line. So that's going to be called the angle of incidence, and that's going to be called the angle of reflection, and we know that the angle of incidence is always equal to the angle of reflection. So if we had a couple of mirrors, and let's see here if I can make some normal lines on this. So we got a normal line here. And then let's say that we have a light ray and that's incident on this. And let's say that this is incident at 30 degrees, right? Question, what would be the angle that it would reflect off mirror 2 with? And let me label these mirrors real quick. This would be mirror 1, and this would be mirror 2. And so what angle would it reflect? Well, if we just use geometry, then we know it's going to reflect at 30 degrees here also, right? And then it's going to reflect off like that. In the middle is going to be another one of those. So we have an angle of 30 degrees here also. Let me erase that real quick. And let me write it down here just a little bit further down so you can. So that's 30 degrees there. So what's this angle right here? Let's make this angle a different color. What's this angle right here going to be? Well, we know that this is a 90-degree angle. So we know this has to be 60. Or we know, hold on a minute. We know this has to be 60 here. Well, I can't get my pen to write. There we go. How do I know that? Because 30 plus 60 is 90. So that means this has to be 60 because alternate interior angles are equal. Or we could have also said that this right here was 30 because of alternate interior angles, and that was 60. So guess what this has to be? This angle of reflection has to be 60 degrees. So that'd be the answer to that one. That'd be a little more complicated idea. So that's the flat mirror, the basic thing we're doing with that. The other kind of mirrors we have is we have a convex mirror that would, well, that's not very good. That would look something like that. And as light rays, and let's make some straight light rays here. As light rays come into this, they're going to hit it and they're going to diverge. In other words, they're going to go outward like that. Well, when we make a dotted line back to the back here, there's a place where these cross. Yeah, there's a place where these are going to cross back here. The place where they cross, that's not exact, is called the focal point. Well, this is a negative, so what do we know about these guys? We know they have a negative focal length. We know that they make only a smaller virtual image. We know a virtual image is one that's upright. And so if we know the focal distance, we can use the lens maker's equation, 1 over f plus 1 over p plus 1 over q, to find either object or image distance or focal length, depending on what we have. So that's the convex. This is convex mirror. This is flat mirrors. And then we have one other kind of mirror that we'll look at, and that's concave. And when concave mirrors, well, first of all, I don't really have this on here. It probably would have helped me. We have something called the principal axis. And on that principal axis, we have the focal point and the center of curvature. Let me get these moved down here. Oops. Didn't work very well. There we go. Evidently I got two images here. All right. So something like that. Anyway, this would be the focal point. Focal length, focal point. This would be R, or center, C for center of curvature, which is 2 times the focal length. So when we have a light ray that comes in to this, if it's parallel with the optical axis, then it's going to reflect through the focal point. And we just need 2 of those, like that. Now, this F is positive, and it can have larger virtual or smaller, larger, same size real. Smaller, larger, same size real. So if we look at what's going on here with the concave mirror, when I say small, large, or same size real, or larger virtual, it's kind of a specialized, let me get my pen going up here. It can do a lot more than the convex, and here's what I mean. So if this is my focal point, F, then if I have an object right here, then the image is going to be a larger virtual back here. In your book, I think it's on page 460. Let me be sure. You really need to look over page 460. Yeah, page 460 has a bunch of pictures that'll really help you. So if I'm on F, there is no there is no image, and here's C or R. If my object, let's make the object blue, if my object's between F and R, it's now a real image. And the image is, of course, upside down because all real images are upside down. It's upside down and larger. All right, if I move this image, this object, this direction, then guess what? The image moves the opposite direction, so that when I get right here on R or C, then I have an image that is the same exact size in the same place. I keep moving it, the object to the right, and the image keeps moving to the left. And when I get beyond C or beyond R, then I have this smaller real image. And that's kind of how the concave mirror works. Again, it does follow the lens maker's equation. F's always positive on it, F's always negative on this one. So it depends on what kind of mirror you have. And I think that's a good review.